Yeah, oh, that's awesome. Good. Thank you. Hold on. I will say, I love it. Wait a minute. Where? Good after. Yes. Hi. Hello. Hello. Good afternoon. Thank you. Good afternoon, Jose. Good afternoon, All Smile. Hi, Sarah. Hi, Sarah's cat. I think beautiful. Um, I don't know if that, but does Sarah's cat have the calculus prerequisites? That's the, okay. Thank you very much. Okay. No, that's awesome. Hi, Kirsten. Good afternoon, Brian. Hi, Sumaya. Hi, Montserrat. Oh, wait, people coming. So, good afternoon, Stephen. Still, oh, top of the afternoon, Abdel Rahman. Okay. Oh, and here comes the board. Okay. Thank you so much for, okay. This, you guys are great. I really, so apparent. I didn't even have, okay. Well, I'll get rolling. We have like a half a class today. I totally apologize. I mean, a half the class time. I apologize for that. I really appreciate that all of you seem to have gotten this message. I mean, it seems like you got the message. You're still here. I appreciate it. I didn't even have time to do one of these. You get points for confirming things. Oh, funny. Okay, okay. Yes. Okay. Okay. So I'll get straight to it. So all smiles. So anyway, I'm sorry I had a thing that was unexpected, but here we are. And we'll get straight to all smiles question. Actually, and hello to anybody I didn't say hello. I'm sorry. Hello, Emily. If I didn't, hello, Katya. If I didn't, hello. I think I said Jose. I think hello, Gianna. If I didn't, hello, Euban. Hello, Jada. Okay. So hello, everybody. Yes. So again, I'm sorry for this crazy. We're only going to have half of a synchronized class today. Technically, the format of this class is mixed synchronous, asynchronous. So sometimes we have to do things asynchronously. Today is one of those times. It's funny that Osmael asks about Big Old Duck, because here's the deal. The whole point of today's class is 100% meant to go over the big old duck problem. That's entirely what we're here for. And that is for technically it was due today. And if I have a moment in a second, I'm going to acknowledge and thank the people who actually did try it. It was technically due today, but that's and so anybody who tried it or ran into difficulty or got answers but isn't sure, you'll get some satisfaction today. That's entirely what we're talking about. It's problem 6 from homework 6. But if you haven't gotten to it yet, still, just again, I always want to make clear, if you haven't gotten into it yet, it's no shame, it's no public critique, it's no F or anything like that, or no points deducted. You still want to do it. Like, we're just going in our pace. I'm behind, you're behind. We just do the next thing whenever you get to it. You still can and should do this problem. And so today, I'm going to check in a sec. Oh, good afternoon, Jasmine. Awesome to see you. Those people who did it already will have the advantage of maybe understanding better what I'm slightly. They might already have things in mind that hopefully I'm going to address, or that they'll ask, and that this will, like, they'll have they'll have more of a mental jump on what I'm saying. But those of you who have not done it yet, this class is for you too. This is not a punishment for not doing it or anything like that. And hopefully you can get a lot out of what we're saying here today. And not only you can, but you still should hand it in. And yes, with the benefit of whatever we say today. And oh yes, live conscription, live conscription. Yeah. And any of you who did do it, and then you want to correct things from today because you did it, that's fine. Just leave your old draft as well. Even if you want to write me a note that says, I only want you to look at my newer draft because my old draft is embarrassing or whatever, fine, it'll save me up, but I'll at least see that you did it twice and that you tried really hard to get the first attempt in on time. Like, that's only to your benefit. All right. So we're going to do that. So we're totally going to talk about Big Old Duck, which is problem 6 on homework 6, like the last problem of homework 6 today. I will say right now, we're still not talking explicitly about exams or anything like that. But when you finally have an exam, this will be on it. Just so you know, this problem in some form will be on it. So it is good to pay attention today, one day or the other. Now I'm going to try to go a little fast because we only have half the period. But one thing I want to emphasize, given that this is a mixed synchronous, asynchronous class, absolutely. I mean, there have been a couple of times in the past where the morning section, they had to be canceled and they just watched the video of your class. That's happened once or twice already. Today is like the reverse. I'm going to encourage you right now and remind you right now that I'm going to go a little fast here. I am going to go a little fast. But I'm going to make sure you get answers and make sure you see basically what I'm doing with this problem. But All of the notes on this problem that I made will be uploaded to Google Classroom, of course, when we're done. So the PDF will be full and I would highly encourage you to watch the video of the morning class once it's posted. I'll put a link also to your Google Classroom. Like, watch that video because it'll be the same material, but maybe go a little slower and a little bit more comprehensively. That might be better for, it just might be clearer for some of you. Okay, so just, I can't. And if you want to, I'll open up a portal. Maybe if you want to send me a screenshot that shows that you tried to watch that video, maybe we'll give points for that too. But okay, that said, yes, it's all about big old duck. What's on the board here is what I'll explain. Don't overly, what's on the board here may look like new equations. It's not new equations. It is old equations that, oh, sorry, someone's here. Sorry. Okay. What's on the board right here, you might the top equation is an equation that we're getting used to as of a couple of weeks ago. And it just has Y's written in instead of X's. And then it has V naught subscript Y. And then instead of an A, it has a G, because what that equation there is just saying, it's just an example of taking an old equation, X equals 1 FAT squared plus V naught T, and applying that one-dimensional equation that we were often talking about in the x-axis, applying it to the y-axis. It's just applying an old one-dimensional equation to a new situation in a different one dimension. Instead of the x-axis, it's the y. Instead of just any old constant acceleration, we have the acceleration due to gravity during free fall, i.e. lowercase g. So don't be thrown by that. Just realize it's just an then this is what happens in physics. It's just an application of an old equation. Then I rearranged it to solve for t. I use the quadratic formula. You'll see why in a moment, because it comes up as a way of solving the big old duck problem. But I'm just trying to get you more and more used to that. Once we have these basic equations nailed down, we use them and rearrange them and reapply them all the time. It's not about having a million new equations in this class. It's about knowing certain equations really, really well and being really flexible with them. So honestly, what's written on the board right here, I'm about to turn the page, but what's written on the board right here is the main ideas that I use to solve the big old duck. It's just old equation written for the y-axis and rearranged to solve for time. And then another old equation, displacement equals average velocity per times time, rearranged and applied to the x-axis of the big old duck. So it's here's, I'm going to slow down in a second. I'm going to turn the page in a second. Just someone's in the chat. What's that? Oh, hi, Mariam. Good to see you. Sorry, I kept you in the way. My bad. And again, to all of you, thank you for being here for this shortened period. Again, anything I don't say or I say too quickly will be in the notes that will be uploaded and will be in the video of the other class section that I encourage you to watch. Now, wait, what does it say underneath these equations? Well, it says this. I'm going to turn the page. So again, for anybody who's just tuning in now, this is all about the big old duck problem, problem 6, homework 6, whether you did it or not. It's what I'm talking about now. And here's the key principle for solving that problem, the key GDP, so to speak, the key idea to put in step 3 after you've done step 1 and 2 to solve the problem. The key is yet a new adaptation or application of Galileo's principle of relativity. I'm bringing that up again. You'll see it. Every new idea we do in the course is some kind of new extension of this basic idea that the Earth moves, but we don't feel it. Like literally everything in physics in some weird way comes back to it is possible for us to believe that the Earth moves at 65,000 miles an hour past the sun, and yet we can never feel it. That's the principle of relativity, that all velocities are relations between pairs of objects, not properties of single objects, right? And there's many different ways to say that principle, and each new way or new form is like a new set of equations or a new chapter in physics. The original form of that idea is that the laws of physics are the same in unaccelerated reference frames or inertial coordinate systems. The physics laws hold in this coordinate system just as well as they hold in this coordinate system, just as well as they hold in this coordinate system. They hold in the x-axis just as well as they hold in the y-axis. So this is a very important idea. And I'm about to turn the page in a second, but here's the deal. With the big old duck problem, which is our first big, real hard, it is a hard seeming problem. Like it's totally doable, but it certainly seems like a lot when you first look at it, I think. It seems very involved. It's very, and part of why the big old duck problem is hard is a similar reason to why lab four, which is very much, oh God, hold on. What's going on? Sorry. It's hard in the same reason, or for a similar reason to the reason that lab 4 is hard, which is that suddenly we seem to be in a two-dimensional world. Lab 4 and the big old duck are the first two, or it's the first lab situation and the first theory situation, where now we're being asked to analyze physics. Did I just lose? What's going on here? Excuse me. What's going on? Okay, where we're being asked to analyze physics in 2 dimensions of space. Do we have equations for that? Do we have information or practice in that? It would seem no, but but we have Galileo. So here's the principle. Here's how we do 2-dimensional or even 3-dimensional or 4-dimensional, n-dimensional, any number of higher dimensions in a problem. We take the Galileo idea that says that the laws of physics hold in every coordinate system. And in fact, any one axis is a coordinate system. So they apply the same way in every axis of space. So Galileo principle of relativity, form number 5. Here's form number 5 here. It's a thing to know for this class. It's a new way of saying and applying an old idea. It says, and I'm reading the blue part on the board. Look, if you're suddenly facing a 2-dimensional problem like big old duck or like lab 4, where things are moving this way and they're moving this way, right? They're moving in a plane. What do? You say to yourself, because of Galileo, you say, every n-dimensional problem, okay, n means the number of dimensions. So in this case, like 2, you say every 2-dimensional problem or experiment in physics is just, in fact, 2 1-dimensional problems occurring independently, yet simultaneously. This is the key insight. I'm going to turn this into equations and math and answers in a minute, and we will solve this problem in the total of 25 minutes that we have left. But I'm saying, big old duck looks intimidating because you got this thing flying across the sky like this, and then you got this shot that has to go up and meet this duck. You've got 2 dimensions of physics happening at the same time. But the key insight is that's exactly all and what it is. It's 2 worlds of physics, 2 little reference frames or axes in which our standard 1-dimensional physics equations apply, and the equations will apply independently to each axis. That is, the presence of the y-axis will not affect the way our standard equations work in the x-axis, nor vice versa. Each little axis is like a little number line, just like homework number 1, and we just apply our knowledge and our equations to that little number line as though it's by itself, as though it's not being affected by anything else. But we recognize that those 2 independent worlds, those 2 independent coordinate systems of y and x are both, they're happening independently, but what's making it one big problem, one big phenomenon, is that they're happening at the same time. This is the insight. So what we're entering now with this problem and with lab 4, we're entering the next topic of physics called 2-dimensional kinematics. Okay, like if you were looking at a book, it'd be the next chapter in the book, 2-dimensional kinematics. And eventually that means we have to introduce things called vectors. But the first insight as to how to solve any 2-dimensional problem is to realize that a 2-dimensional problem is just 2 1-dimensional problems happening independently, yet simultaneously. That is the insight for all of dimensionality and vectors to come. So how does it apply? Okay, that's a major point. So how does it now apply to the big old duck problem itself? Well, here is the big old duck. Hello. Okay, here's the big old duck problem. An example of a 2D problem, our first example of a 2D problem. It's homework. And by the way, again, technically, the reason it was just the end of an old homework, this is like the homework is transitioning us to new material now. The reason it's there, though, is you technically don't need any new knowledge to do this. You just have to take your old knowledge and lift it up a level and take it really seriously and apply it. That's always what happens in physics. Reason, again, I'll say this, even though I'm going to say again, like I always say, somewhat defensively, I know I spend a lot of time on the fundamentals of physics. I ask you guys with me to spend a lot of time on the fundamentals. I'm sure it frustrates some people. I always want to acknowledge that. But the reason for it is the whole idea of physics is that eventually physics is not something that we are told. It's something that we are all capable of figuring out the next step. Physics is a way of figuring out things that have not been figured out yet. So that once we really know the fundamentals, every next step in physics is just a new intense application and extension of the old fundamentals. So the big old duck is totally solvable. Like some of you may have gotten it right without this lecture. But those of you who didn't, I totally understand. So hopefully this lecture will help. But we're just going to take our old ideas and extend them. So big old duck. Step 1, diagram and fact pattern. You're given basically a diagram in the actual problem, but here's my diagram. It's a little bit more detailed, whatever. You always have to make your own anyway. And a key aspect of my diagram, besides the pictures and the numbers and everything, is that I'm labeling. I'm using my diagram as an opportunity to label and define the assumptions of the problem. And specifically, now, I've said this before, but like it's really going to start getting important now that we're in 2 dimensions. I'm using this diagram to label my coordinate system choice, my choice of coordinate system. I'm using it to decide what direction is what in a picture, and very specifically, what's positive and what's negative. Remember, in one number line, in one dimension of space, one direction is chosen to be positive and the other is chosen to be negative. It's up to you what that choice is, but you have to make a choice and then you have to stick with it. So similarly here, we have 2 dimensions here. One happens to be the north-south dimension, right? Which I could have written this way you might be used to seeing it this way on a page, but Galileo, I'm drawing it this way on the page. Like a bird flying across the sky could be flying east or could be flying north, right? But if he's flying across the sky, he's flying like north or south or east or west. He's not flying up or down. The duck is flying across the sky in a direction that here happens to be south. He's flying south, so I'm going to call south positive. I don't have to, but I have to call it something. So that's my decision. I'm calling south positive, then north would be negative. And then there's also up and down. East and west happen to have nothing to do with this problem. So that's my coordinate system, south and north, up and down. Up, I'm calling positive. Down, I'm calling negative. That's very important, like to the math, to make the math. It's important that I'm clear about that. Okay, so then I've drawn this duck and I've drawn this hunter or whatever. And so the situation, if you read the problem or if you're reading it now, the situation's a little bit complicated. We have a duck that's flying along. The duck is flying along at a constant, for a while, at a constant horizontal velocity of 20 meters per second to the south. This duck is going, do, 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 do. You're down here, or some person, some hunter is down here on the ground. And at some point when the duck is somewhere back here in the north, I don't know how far back yet, but somewhere, the hunter fires a shot and the shot starts going up, okay? A half second after the shot is fired, the duck like panics or something, freaks out and starts accelerating forward to the south at 16 meters per second squared. So first the duck is going 20, that's its initial horizontal velocity. Then the duck starts accelerating at 16 meters per second squared horizontally. And the shot is going up and the duck is accelerating to the south. And the fundamental, and what we want the shot to hit the duck. And the fundamental question is for the shot to hit the duck. Okay, wait, so that's, so that's my step 1, DFP. There's my diagram. It's a little clunky, but there's all the information on my diagram, particularly labels. And particularly it's making it clear that I have a plus minus choice for each axis. On each axis, there's an independent, separate choice of what positive and negative mean for that axis. Right, so all that's labeled in my picture, that's step 1, DFP. Then step 2, WIQ, the question is solve for X. I mean, the question is, what is X? How far back to the north is the duck at the moment I fire my shot? Or put another way, when should I fire my shot? Where should the duck be when I pull the trigger, given all these facts, such that I actually hit the duck? That's a question. Is it an easy question? No. Is it a very forensics question? Oh, yes, right? Like here we're now using our kinematics and our knowledge. Instead of to predict the future, we're really trying to retrodict the past. We're trying to say, given that something's happening now, what did happen back then? Where was the duck if I fired and hit him, right? It's a very It's silly, but it's a very crime-solving type of application of physics because we're actually predicting the past given the equations as they were manifested in the present. Okay, so the question is determine X such that the duck hits the shot. Okay, so I've done step 1, step 2. I'm turning the page. Step 3. All right, so now I got to get really rolling with this problem. My GDP, my general definition and principle, my principle that's true even before this problem starts, but that I think is topical to the problem, is exactly what I said 2 pages ago, is Galileo's principle of relativity, the new form, form number 5. And by the way, even if when you tried to do this homework, you didn't know that or know those words, that's okay. This is my cleanest, clearest way of saying this now. But I'm saying the principle here is that one-dimensional equations are meant for each dimension. So we're going to use what the real principle I'm saying is we don't need new equations for this. The real principle I'm saying is we don't need new knowledge for this problem. We just need to use our old knowledge carefully and independently. I'm saying by definition, if we want to know when to fire the shot such that the shot hits the duck, what we're really asking is, how can we arrange things? What are the numbers to solve for such that the shot and the duck arrive at the same place at the same time, right? We want shoom. Well, that didn't use. We want shoom. We want the shot to hit the duck. We want the shot to get to a place that the duck gets to at the same time, which means we want this motion, this one-dimensional independent physics thing, this shot going up to a certain height, to take the same amount of time as the duck traveling its horizontal distance. That's the key to this problem, is we want each thing to take the same amount of time. Now, the same, so if we do our physics equations, we're going to plug in the same number for t in the x-axis as we do in the y-axis. So why don't, if we could figure out what t needs to be in one axis, let's just solve for that and then plug it into the other axis and we'll be done. That's what we're going to do. If you think about it and you step back, and this is where the first page of the notes comes into play. If you step back and think about it, duck or no duck, if I fire a shot at 30 meters per second up in the air, I fire it and it starts going. I'm not I fire it, I give it an initial velocity and then I let it go, it just goes up. This is exactly the kind of problem we were talking about last week and the week before. This is just like throwing a ball in the air at 30 meters per second. Now, duck or no duck, I know the physics of that. In fact, we could plug in the equation y equals 1/2 at squared plus v naught t, or x equals 1/2 at squared plus v naught t. We can call it y because we're going the y-axis now. And we could figure out everything we want to know. We know the a, it's free fall. If we're calling down negative, the a is negative g, negative 10, approximately 10 meters per second squared. So I'm going to tell you right now, if I fire this thing up at 30, I know, even before the duck comes into play, that it's going to start at 30 and it's going to lose. Like, you could do this with equations, but once you get used to this, follow me, you could do this in your head like I'm about to do. You fires up at 30, so it's losing 10 every second. So it's going to go like 30, 10. I'm sorry, no, it's going to go 30, 20, 10, 0. It's going to take 3 seconds before it reaches a peak height. Duck or no duck, an object would take 3 seconds before it gets to a peak height if I fire it up in gravity, right? And that means it's going to go from a speed of 3 seconds, because 30 divided by 10 is 3, because v equals at plus v naught. So it's going to take 3 seconds, but I'll go a step further. I'm just talking now to give you perspective on this. If it's going to start at 30 and run out of speed to 0, that means with constant acceleration, then its average speed would be 30 plus 0 divided by 2, right? We can use that equation because it's constant acceleration, free fall here. So 30 plus 0 divided by 2 is 15. So anything that goes up will go up at an initial velocity of 30. We'll go for an average of 15 meters per second. It will do that for 3 seconds, because we just said that, 3 seconds before it runs out of its steam. So its peak height is going to be 45 meters. I know everything about this object before the duck even comes into play. It should be going up for 3 seconds, reaching a peak height of 45 meters, and then coming down. But what the problem wants me to solve for is the time it takes to get to a height not of 45 meters. We want to know how much time it's going to take to get to a height of whatever was given in the problem, which I believe was 40 meters, right? So I'm just going to plug into the equation. Y equals 1 at AT squared plus V naught T. Like I'm assuming Y naught is 0. I'm assuming X naught is 0, right? So I'm saying Y equals 1 at AT squared plus V naught T on this page here. But I know Y, it's 40 meters, I was told. And I know A, it's free fall, it's negative 10. And I know V naught is 30. It was given in the problem. So I'm solving for T, right? Unusual, but totally fair. So I'm just going to, so it's a quadratic equation. I'm going to do the quadratic formula as you saw on the first page. I'm going to do the quadratic formula and solve for T, right? Or if you, and you can't see that because of the thing on the bottom, but I'll publish these notes anyway, but I solve with the quadratic formula and I get two answers because there's two mathematical roots to this quadratic. I get 4 seconds and 2 seconds. Or if you don't like the quadratic, you could just factor. I just did that quickly. You could factor and you'll get two answers, 4 and 2. Two answers for the time. Now, by the way, we're not done with the problem, but we're almost done and we have 12 minutes. What we have so far is the amount of time that the shot would take to get up to 30 meters, regardless of any duck. Like, how am I using the duck knowledge right now? The only way I'm using the duck knowledge right now is I'm saying, well, the duck is at a level of 30 meters above the shot. I'm not using at all what the duck is doing. I'm just saying that I'm doing one dimension at a time, one dimension independently. I'm saying that this shot has to travel 40 meters in free fall, under the influence of gravity slowing it down. It has to travel 40 vertical meters from an initial velocity of 30 meters per second. So I'm just plugging in the equation, if you like, the equation we spent 2 weeks developing and practicing. But also, and I'm getting two answers. I'm getting two answers for that time. The time that this shot would be at a height of 40. Now, why am I getting two answers? Well, mathematically, because it's a quadratic. I mean, it's a second degree polynomial. It has two roots. Okay, but that's math. So what? Physically, what the math knows is that the thing has that it's being fired up. In gravity, acceleration constant that's pulling it down. It's being fired with positive initial velocity, but it's subjected to an acceleration that is constantly, like forever, negative, right? So they're in conflict, the initial velocity and acceleration. According to the math doesn't know there's a duck. It just knows I'm just asking at what time will this object be at a height of 40 meters? Well, this object, if it's got an upward initial velocity and a downward acceleration, this object is definitely, according to the math and the physics, this object's going to go up until it runs out of speed, and then it's going to come down, right? Necessarily. In fact, we just figured out in our heads a minute ago that this object, if there were no duck, would go up for 3 seconds, stop, and then come back down. The math and it would go up to a height of 45. In 3 seconds and then come down. We just did that in our heads, or I did 2 minutes ago. This math says, well, if you want to know how much time it's going to take to get to 40 meters, it's going to hit 40 meters before it gets to its peak height of 45. It's going to hit 40 meters, according to the math, a second before. At 2 seconds, it'll be at 40 meters. And you can check that with your equations if you want. In 2 seconds, it'll be at 40 meters. But then 1 more second to be at the top, and another second, it would be back down at that same height again. 4 and 2 are symmetrically surrounding 3, which makes sense because an object shot up at 30 should fully run out of speed and get to a peak height at 3 seconds. So we're saying at 4 and 2 are the two times that it will attain a height of 40 meters. Just one of them, the 2 second time, means on its way up, and the other is on its way down. So we get 2, and no one in the problem ever said you had to shoot the duck. No one ever said in the problem that you had to hit the duck while you're on your way up. They just said we want to hit the duck. So the physics and the math are saying, well, there's 2 opportunities. You could hit the duck in 2 seconds while you're on your way up, or you could keep waiting and hit the duck. If the duck is in a different place, you could hit it 4 seconds. Either way should work. So what am I going to do with these 2 times now? I'm going to turn the page. We're almost done. We are almost done, and we're almost done. That was all the y-axis. Like that whole y-axis was just doing physics that we already know about what a shot of how much time it would take a shot to make it to a height of 40 meters if it were shot up at 30 meters per second. That's what that was. Now I go over to the x-axis and I independently look at the x-axis and I say in the x-axis, okay, first of all, there's this kind of annoying fact that first the duck for a half a second is just cruising along at 20 meters per second constantly. So I just say, first off, there's no acceleration or anything. So it's just displacement equals average velocity times time in the x-axis. So I put these little, so now I'm starting to put subscripts on my equations just to make clear which axis I'm talking about. Because again, all of the equations, we're not developing new equations. We have all the equations we need now. We've all the equations we need for any one-dimensional physics problem. So I'm just saying we're doing two separate one-dimensional problems here, but we're going to put them together in time. So so I put subscripts to label which axis I'm talking about at any moment. So in the x-axis, x equals average velocity times time. 20 meters per second is the average velocity, the constant velocity. It does it for a half second. So no matter what, the duck is going to travel 10 meters no matter what before it even starts accelerating, right? So that takes a half a second. But then we found out that we've got 2 seconds or 4 seconds to play with entirely for the shot to go up and down. So the first half a second is just taken up with the duck just going along a constant velocity. But then there's more time left over. Like if I'm going to take a total of 2 seconds, 2 minus 0.5 is 1.5. If I'm going to take a total of 4 seconds, 4 minus 0.5 is 3.5. So we've got 1.5 and 3.5 to play with left. So now we just take into account the duck's acceleration. We say now in the x-axis, x equals 1/2 16 times 1.5 squared plus 20 times 1.5. In other words, the equation, well, I don't know, you're not going to be able to see, well, the equation that I'm using here is still, I can't fit in. It's still the x equals 1/2 at squared plus v naught t. I'm saying that that same acceleration equation applies now in the x-axis independently from the y-axis. But notice in the x-axis, so I'm using this equation again, the same one I used in the y-axis. Only we're in the x-axis now. So it's not free fall in the x-axis. It's not gravity. It's not -10. It's that duck acceleration, that constant duck acceleration of 16, right? And that's not, right? Yeah. Okay. So I just plug in 1/2 times 16 times 1.5 squared plus 20 times 1.5 equals 18 plus 30. So I get x1 equals 48 meters. That's how far the duck traveled. So what I'm doing here is I'm saying, the key point that I'm making is I'm saying that this has to happen in the same amount of time as this. What we're trying to solve for is the x displacement along this axis. So our method here is we're saying, find the amount of time that this takes, then assume that that exact total amount of time is what we have to play with over here. Assume that the x-axis and the y-axis occur at the same time. So use one axis to solve for the time and then plug that time into the other axis. That's what we're doing here. So I'm taking the total time and plugging it into the equations of the x-axis. And in the x-axis, I'm finding that the duck would do 48 meters while it's accelerating for 1.5 seconds, but it had already done 10 meters. We just figured out on the other page. It had already done 10 from its unaccelerated motion. Like, in other words, for the first half second before it realized that it just heard a shot and it spazzed out and accelerated. So answer one to the whole problem, and we still have 5 minutes, but we have one of the two answers. Answer one to this problem is 58 meters, meaning that you should fire, that says fire, that you should fire when, like, answer one to this problem is if you want to hit the duck, then as soon as the duck is over there 58 meters to the north of you, as soon as the duck is 58 meters to the north of you, pull your trigger. And then at that moment, the duck will keep going along for 20 meters per second for a half second. It'll do 10 meters. Then it'll realize it just heard your shot. It'll spaz out and accelerate, like as we were told. And it will have, and it'll undergo accelerated motion, and it will cover exactly 48 meters in that remaining 1.5 seconds that it has to get to where you were, right? In other words, if you do it right when it's at 58 meters, that's exactly the right amount of time. That's exactly the right amount of distance to have the duck arrive at your coordinate right when your shot arrives at that coordinate. That's answer one. But the other answer is, oh, you could instead give the duck 3.5 seconds of accelerated motion, because you could fire when the duck is all the way wet back here. Like I just did the exact same math, but just plugged in 3.5 instead of 1.5, because I'm taking my other route for time now. I'm saying, you know what? If the duck is 178 meters back there and we pull our trigger, that would also work, because the duck would be going for a half a second, do its 10 meters, and then it has 3.5 seconds more to be accelerating. What will happen is it's a lot farther back. It's accelerating for a lot longer. It'll get around here. My shot will be up to its height, and I'll think, oh no, darn, I missed it. But my shot will keep going up, and the duck will keep going, and then my shot will come down and hit the duck. It'll get back to the duck right on its way back down. So option number one is hit the duck directly on the way up. And if you want that, you fire when the duck is 58 meters back. Option two is fire much earlier. Wait till the duck is 178 meters back to the north. And in that case, you'll hit the duck on the way back down. Now, those are the two answers to this problem. Again, I talk maybe a little bit fast. I don't know. It might have been perfect for some of you. If anything went too fast or whatever, you can watch the other class video. I will also post this video, obviously. We still have 2 minutes. I'm just summarizing here. But there were a couple other, one sec. So there were 3 questions that were asked by the duck. Part A were, where should the duck be? And I'm saying there's actually 2 answers. Here are the answers: 58 meters to the north and 178 meters to the north. The other question it asked right after that was, why are there 2 answers? And I've answered that. The reason is because there's actually 2 answers to the possible time. And that's partly because of the math, but really because of the physics, because the shot will go up and then it will come back down. Then it asks, what if the duck had a negative acceleration? Really good question, actually. If the duck had a negative acceleration, so it was slowing down while it was going, that's totally possible. And that's an interesting other question. Then the duck would have slowed down, hit 0, and then started going back. And just like, then it would be like gravity, like the problem we done the other day. So then the duck would make a round trip and your shot would make a round trip. So it might, and I want you to be able to picture that if it had been negative 16 instead of positive 16. But even there, if you work it through, you'll still only find that there's still only 2 possible ways to hit the duck. There aren't 4. I'm not going to get into that details right now, but there still would only be 2 answers to that. We're just about done. We have like 30 seconds left. But those are the answers to the question. That's how you do it. The key point to the whole thing is you just use your old equations from one dimension, but you apply the equations and the knowledge to each dimension independently yet simultaneously. That's how you do 2-dimensional problems in general. Those are the answers to that problem. Hold on, we're just about done. You can obviously stay for a second if you have questions or anything. I'm going to post all of this, of course, but I do want to just quickly say I'm totally aware everybody's fine whether you did it or not. Hopefully you got something out of this class and you will do it. But I do want to acknowledge that if your name happens to be Stephen or Brianna or Brian or Miriam or Abdel or Sarah or Gianna, I'm totally aware that you totally did kill yourself to get this thing in on time. And I appreciate that. And whether you got, and you can redo it if you want, or if you nailed it, I'm even more impressed. I'm impressed with everybody. I'm happy with everybody, but I did just want to acknowledge, I do know it if you're turning these things in like earlier or whatever. Okay, sorry. And Smile has a question. Sorry. But the rest of you, but thank you very much. I'm staying. I'm not going anywhere for any questions, but I think Smile is one of the people that has a question. So the rest of you can go if you want, or stay for all. Anyway, Smile, please. I'm sorry.
Oh yeah, my question was quick about that last part. If his acceleration was backwards, the only way you would have 4 answers is if the highest degree was 4, right?
Very good. Yes. Wow. Yes.
Okay, just making sure.
You are awesome. Yes, we should hang out on the 4th floor more. No, yes, awesome. No,
all right, thank you. That's all.
Thank you.
I realized that I sent the wrong page, so I unsubmitted. I'm gonna resubmit it right now.
Okay, great. Awesome.
Thank you. Have a good day, Professor.
You too. Thank you. That's great. Okay. Bye, Emily's cat. Bye. Oh, have a good day, Euban. Thank you very much. Bye. Thank you. And thank you, Emily's cat, too. Okay. And Emily, you're good, or or Emily's cat, you're good. You have the prerequisites. You know calculus. You're good. Okay. I'm stuck. Goodbye. Thank you, everybody.